All right. So I'm Christian. Thanks a lot for having, on behalf of the three of us, thanks for having us here today and popped into our little group. We're really pleased to present to you these projects. I'll kick things off with mine, which is titled, you can go, oh yeah, leave it there, that's right. 3D printed puzzles for STEM outreach and cultural preservation. And it researches the use of modern digitisation techniques such as 3D scanning and photogrammetry and computer aided design to reverse engineer and then recreate tangible historical assets that can be placed into the hands of users as object-based learning tools. But yeah, look, first a little bit about me. I come from an automotive background. I spent a decade working as a tech in specialising in historic and collectible vehicle restoration. And nowadays, in addition to my day job in life sciences, I run a small engineering design and consultation business, and we have a real sort of focus on using these like modern techniques to reproduce parts and components for historic vehicles, but also working with clients to kind of create these learning opportunities and drum up some interest in the field. Next slide. So yeah, this project really explores how to create these learning opportunities, but particularly for younger students through modern design and advanced manufacturing methods, while simultaneously drawing attention to significant historical achievements that really led us here in the first place. The concept originated as creating a toy car that could be broken down into its basic parts and then reassembled. Next slide. So yeah, ultimately it developed into a 3D printable puzzle of this 1934 Ford Ute, and really aimed at providing STEM outreach opportunities for early primary school students in the Greater Geelong region here in Victoria. The model itself is designed to be a historically accurate scale representation of that ute, and is really positioned to offer a tactile, object-based learning opportunity that heralds a design of immense cultural significance for the region. So, as a bit of a background, Geelong is the second largest Victorian city outside of our state's capital, Melbourne, and from its inception in the early 1900s, really established itself as one of the leading manufacturing centres in Australia. And it was spearheaded at the time by what is now the defunct Ford Motor Company manufacturing facility, where in 1934, a young designer named Lou Bant coined that first ute. Next. And yeah, I mean, it's really significant. It's really important to consider the significance of that achievement. That ute went on to become a staple of Australian culture, as we all know, and a global icon. Yet the history and the manufacturing identity of its birthplace, as we've sort of seen with many former industrial hubs around the world, is now becoming overshadowed by this modern push for innovation and change. And 95% of the research participants viewed the concept of integrating manufacturing traditions and cultural heritage into the curriculum of young people in the region as one of really great value to the future of the community. By helping to highlight the significance of those past innovations and then to use them to encourage younger generations to get involved in progressing the region's sort of innovative goals for the future. So to create something tangible that could be demonstrated within local museums or even manufactured and built within classroom environments could really importantly increase that exposure and awareness to the cultural significance of the local design and engineering, but do so by showcasing the most iconic of those inventions in a really unique way. So you can hit the next one, Mensa. Thanks. Yeah, so to gain an insight into why that reverse engineering process is actually necessary, it's really important to identify the fundamentals of the tech. So in basic form, the 3D scanner maps the object or surfaces being scanned as a set of data points in space, and then they're all joined together with lines, converted into polygons and triangulated, as you can see in the top three images there, into what's called a surface mesh. But the problem with this is that that's not editable in that format. So and also the fidelity of that output is dictated by the granularity in which those mesh sections are interpolated between each other. So basically how fine the rendering software can process the data. As such, a high resolution will inherently allow for greater accuracy to the original object, but then it comes at a cost of long rendering times and strains on computer hardware or large file sizes and so on. So it's really about picking your battles. And yeah, like in the bottom 3 images there, you can see that sort of the fidelity of the scanned output was simplified in the center image to be acceptable for like a gamification and virtual reality use. But when using that same sort of resolution in 3D printing, the surface quality and the aesthetic is actually really poor, and it's not suitable as a representation of that original object. Next slide. So then to enable really high quality prints, but with a low processing cost, it involves using this complex geometry basically as a template and then creating solid editable bodies in a native CAD format from there. So better defining that process, that 3D scanning to the CAD framework was basically the most critical aspect of the project. And the goal was to try and develop a methodology that could be transferable between many different CAD packages, and one that really utilizes skills that can also be readily taught on a fundamental level to really enable anybody with access to even sort of basic and free software the ability to do this type of work themselves. So next slide. And yeah, look, I won't go too much into the details, but because we'll be here for hours, but encouragingly, in testing the developed framework on multiple entry-level users with no sort of formal engineering or CAD experience, they were able to recreate some of the more challenging components of this model in about a quarter of the time that it took me to develop it in the first place. And while this is obviously really subjective, it offers a great early insight into the potential for, say, a savvy educator within a classroom or a museum environment to pass on this type of skill to young users who, thanks to multiple online and open source data repositories these days, can really scan and access, modify and create their own interactive scale models of historical objects and industrial heritage. So next slide. Now this is a video it's going to play. Yep. So this approach really allowed for a very targeted final design, which I actually 3D printed at home in an environmentally sustainable material called PLA, and using what's known as the FDM technique. So it's basically the most common sort of 3D printing technique available to the layman these days. It weighed in at about 500 grams in 1:15 scale and consists of 15 individually magnetically interfacing parts, and were engineered and validated as safe for use within the target age group. So further to this, the workflow from that scanning to CAD was really well defined and easily repeatable within a typical classroom environment using virtually any basic CAD package, and then access to an FDM printer of the appropriate size and some off-the-shelf componentry. You can skip to the next one if you like, Mazda.
It's jumping, that's why sometimes, but
I think it's got like an automatic
yeah, true.
slide.
That's why I'm following.
Yeah, but that's all right. In addition, a secondary prototype, which is pictured here, was printed using Deakin Uni's powder bed printer to demonstrate the potential of full color and textured 3D printing. And it's a much sort of higher quality, high fidelity process that can be used for artifact preservation, and really sort of showcases where the technology is likely to be heading in the coming years for basic users. Currently, it's pretty cost prohibitive for smaller institutes and hobbyists, but it's not beyond the reach of larger educational institutes like museums, for example. So there really is a lot of potential there. You can hit the next one. Cheers. So yeah, look, what I find, I guess, the most captivating about this, well, really any form of 3D printing, is that while the method, or each method has its limitations, the limitations themselves actually offer a really fantastic and sort of unique opportunity for users to think beyond the form and then to kind of watch something complex be created essentially from nothing in front of their eyes in real time, with the inherent fingerprints of their own design decisions. And the perfect example of that, which is often considered an unsightly hallmark in 3D printing, are these visible surface build lines. And through lots of our sort of hands-on experience that we've had with students and so on in the last sort of 12 to 18 months, it's often actually a really fantastic discussion point. And many users of the puzzle have expressed this intrigue, and it attracts these fantastic educational and outreach opportunities in terms of really encouraging critical thinking and a deeper understanding of the design and engineering considerations in product realization. So that's about it from me for now. I'll pass over to you now, Munsa, and yeah, we can take any questions sort of as a group at the end. So cheers for that.
Thank you, Christian. So as Christian's experience was very much tactile, hands-on, I put this 3D printed model of a youth in virtual reality. So the research focus is on how to improve this communication, this interaction between the youth as a museum object and the museum visitor in virtual environment. And as we know, virtual reality has been part of car design or at some stages for a very long time, and has rapidly advanced, especially in these 2-3 years, and become really accessible, easy to use, set up from anywhere. So human-computer interaction research in the museum context, it's needed to ensure that this interaction not only works, that it's also meaningful. And what is new here when I'm talking about virtual reality is that interaction happens in a 3-dimensional environment, which is different from traditional interaction with screen-based 2D interfaces like smartphones that we are all really familiar with. And first, we place this 3D scanned youth in different VR environment with very limited interaction. People could only walk around and see it. And then based on this data, we created a cartoon-like 3D model that actually I've used for the 3D for the VR experience prototype. And the next question was how to communicate this heritage value of a now digital object. And based on literature review and formative evaluations, we believe that value is really created by contextualization and interaction. So interaction is important for the interpretation of museum objects. It has a positive impact on learning outcomes, on retention of information, can present and overlay, add new information, trigger an experience, and meaning making. In generally, it offers more, let's say, engaging, exploratory, and personalized experiences. So this to explore this 3D interaction that I was talking about, first we had to design a prototype VR experience. Unique is that we place the task into the context and also evaluated the interaction techniques within the context. So the first image, the task 1, is the first experience that we explored the simple selection and manipulation task. It was evaluated in the scenario of loading a youth with 5 foreign objects that I've talked about in last year conference. And in the recent second experience, we evaluated the proposed interaction techniques for bimanual complex manipulation tasks. So now the task is way more complicated, let's say more complex. And as we know, many everyday tasks require interaction with both hands, like eating with fork and knife and hammering a nail. But the understanding of the design for bimanual freehand interaction is still sparse. And what we explore is the tool interaction in VR. We tried many different tools and tool-specific tasks like nut insertion and tightening. We try many different pliers in virtual reality and found it really challenging to replicate this real-world interaction. Because the things in real life that we take for granted, like picking an object inside the virtual reality, we need to make the users to be able to do this, actually. So we have to design this interaction. And you can do things in VR in many different ways, but actually, what is the most effective way? That's the question, and this presents design and engineering challenges. We selected a task of circlip insertion with a circlip pliers on a shaft. So in the task, you can see the task breakdown underneath. The left hand was used. The left hand was used to pick up the circlip from the workbench, and then the right hand was used to handle the pliers and to actually insert the clip on the shaft that was located on the back of the ute. And the participants tried, this was happening in VR, the participants tried three different interaction techniques under two conditions. Once they actually see only virtual pliers in VR, and the second time they could see the virtual and also hold the real physical pliers in their hands. So we evaluated if this type of passive haptic feedback, like holding a real pliers, improved freehand interaction in VR. But the problem was really to align physical and the real worlds. So physical and the real pliers. That's why opportunities for passive haptic, of course, are limited. But despite those technical and perceptual challenges, most of the participants reported the benefits of feeling the real pliers, like being more realistic and more natural, which was interesting. 21 participants aged 18 to 65 years evaluated the experience at their homes. So the evaluation was conducted at participants' home using Zoom, and we conducted user experience and usability evaluations to investigate this impact of passive haptic feedback on or actually really handling the real physical everyday tool on the impact on the user's interaction. As you can see, they interacted on the pictures, they interacted with free hands. Once they used pliers, and the second time they saw only virtual one. Their hands were tracked using Oculus Quest headset and the camera tracking within the Oculus Quest headset. Participants found the task really challenging because it was more complicated. They thought it was mentally actually demanding. They even felt frustrated and annoyed when they're trying to do something and it wasn't working. But at the end, most commonly used words that described their interaction was actually really positive. They found it engaging, fun, valuable, entertaining, high quality, stimulating, accessible, intuitive, all these positive despite of the challenges they were facing while they were interacting. Yeah, so we could see the potential in virtual reality to simulate the real world tasks to some extent, but the interaction must be very carefully designed around technology limitations and benefits of VR. And this way, museum visitors could have some hands-on experience, for example, on how to fix the machinery without breaking it, and to really get better understanding of how things work. I will pass now the next slide to the Christian to read aloud the anecdote from Henry Ford and Lancaster.
Yeah, thanks, man. So this is a bit of a cheesy segue here into Saeed's paper, but
Yes.
it's a great anecdote from Henry Ford's 1922 autobiography titled "My Life and Work," on his opinion of the English car manufacturer Lancaster. And for our American friends on the line, I apologise, but I won't be attempting a Michiganized accent for this one. But so he says, look, we study every car in order to discover if it has features that might be developed and adapted. If anyone has anything better than we have, we want to know it. And for that reason, we buy one of every car that comes out. Usually the car is used for a while, put through a road test, taken apart and studied as to how and of what everything is made. Scattered about Dearborn, there is probably one of nearly every make of car on earth. Every little while when we buy a new car, it gets into the newspapers and somebody remarks that Ford doesn't even use the Ford. Last year, we ordered a big Lancaster, which is supposed to be the best car in England. It lay in our Long Island factory for several months, and then I decided to drive it up to Detroit. There were several of us, and we had a little caravan, the Lancaster, a Packard, and a Ford or two. I happened to be riding in the Lancaster, passing through a New York town, and when the reporters came up, they wanted to know right away why I was not riding in a Ford. Well, you see, it is this way, he answers. I'm on vacation now. I'm not in no hurry. We do not care much when we get home, and that is the reason I am not in a Ford. So I'll now hand it over to Saif, and he can talk a little bit more about the best car in England.
Yeah, thank you, Christian. Thank you, Manza. So, hi everyone. My case study is about revolve around Frederick Lanchester invention. So basically, Frederick Lanchester, he was an engineer, polymath, and he did many contribution to the engineering industry in general. Including the aerodynamics, the disc brakes, as you can see here in this picture depicted in the right corner. And also he did the first all British car, four-wheel British car. And they mentioned that there is a long association with the royal family. They used the Lanchester's car 80 years ago. So if we go to the next slide, Amanda. So this is the object I choose for my study. It is a petrol electric car. What's so special about this car? It was way ahead of its time. And there is only one prototype at the moment displayed at Birmingham Science Museum. During the development stages, I used the archives in order to do the models. Because at the time I created the experiment was during COVID-19. I couldn't go to the museum, so I relied on these poor little bits. It's not clear yet, but I couldn't scan the car at the time. So the problem with the car, basically, it was very complicated because it was developed 100 years ago. So I use these blueprints to create the actual and the closest model of it. So if we go to the next slide, we can see the details and how the development of the actual. I use programs such as Maya to create this model. First, I created a high polygon model and then reduce the polygon counts in order to make the experiment faster. If we go to the next slide, okay, this is basically if we see the right image, we can see this is the actual image taken from the archive in the Lanchester library. So I went to the library and I met the experts, and we took some data from 1924 or 1927, where the car invented. So based on these images, I created a replica in virtual reality, so allow the visitors to see how the car was invented in 1927. So why I call the experiment as journey to the past. As we can see here, this is the car and this is the garage. So the player got the opportunity to navigate, explore the car, see it from different angles, even open the doors. And there is also because the experiment about interaction, so I used gamification to motivate the visitors during the visits. Storytelling theories implied also to make the experience more enjoyable and entertaining. If we go to the next slide. So this is the one of the Lanchester. This is the Lanchester office. Basically, the player here got the opportunity to see the blueprints of the car, including some of the puzzles. So the player got will face some challenges to make the experience more exciting. So there is some puzzles. For example, here in this room, there is different books related to the car. So the player needs to read, and this way he will be educated while being entertained. So that's why we call it gamification. This is how we evoke the intrinsic motivation during the visits, and also we consider the time during the visits. So it's fixed as well. Next slide, please. So yeah, this is I also implied some methods to make it easier for the player to navigate inside the virtual environment. So there was some arrows, guiding system to make the experience more. It make it easier for people who's not get used to the gaming or background in gaming. So this is so after a while, the data shows that after 4 minutes, the people get used to the experience, the controllers, and the experience overall become more intuitive to use. Next slide, please. So the data collection, there's 3 methods I use. First of all, I recruit participants at Coventry University using a booth there, and also the Coventry Transport Museum. This is where the main study there, because it's connected with the engineering heritage. And also I sent some.
We only have 5 minutes left, sorry.
Okay. So I use also online methods to recruit participants. Next slide, please. So this is one of the pictures. If we go to the next slide, this picture depicts how I recruited expert users at the Coventry University to see how we can improve and enhance the experience before we recruit participants, so we can develop if there is any bugs in the experience itself. Next slide, please. So this is where the expert users at the Transport Museum. So yeah, these are So this slides, it shows a tracking system I use, because we also allow participants to sign a consent form before so they already know about these methods. This allows us to see where is the point of interest during the analysis phases. So yeah, thank you all for listening, and this is all for me. I give you back to Manza.
Thank you, Saif and Christian. So we are ready for any question.
Great. Thank you. Are there any comments, questions from the floor? And also there may be some from our, just go here. You can stay there if you want. I'm just doing this so you can see if there's any people online. Any questions, comments? Is the
everybody's speechless?
Is the new developments in the BANT model that you've now sort of put those new interactions in?
Yep.
Are they going to be now housed out in the museum sector? Like, are they at a site, or are you still developing them?
No, I'm still developing, because my research is focused on interaction technique.
Yeah.
Well, say if it's more on gamification and storytelling. So I'm really narrowing down and looking technically at the specific techniques, and I've conducted evaluation. I just finished them, so I'm doing now the analysis.
Yeah.
But it's not out there.
No.
No.
But
it's only to inform us further, because we are planning to develop further the youth real story, the whole package. I think I've showed only 2 slides in the last presentation last year. So we are still preparing everything for this bigger VR museum experience about Luband and the story of the youth.
And that's basically, there's an impetus to then have that as a public exhibition, or potentially permanent.
Yes.
Yeah.
Yes.
Okay. just I think it's important to make that clear.
So
particularly
all
with those
this
110-year-olds.
knowledge about youth, even from Christian's part of this, the student work they
Yeah.
did, 3D scanning, all this work will inform this future experience.
Yeah, a Christian and probably others like Paul and John and others in the audience that have worked with FDM and other 3D techniques. Feel for you when you get those little anomalies in the model field.
Oh,
But
yeah,
you're right.
there were
Sometimes
many.
it can be quite a beautiful part of the process as well.
Yeah, it's
It-
interesting in interaction, how important is. That's why my research is completely focused on interaction design.
Christian, did you have any comments about the 3D
No,
print?
just in agreement that you know, it can be a real pain to work through those types of issues, but at the same time, it opens up some really unique opportunities to demonstrate different ways of thinking and approaching problems and problem solving, and it's pretty unique to that type of manufacturing process, which is great, and it's something that exists in the hands of a lot of users where other manufacturing processes don't. So,
and FDM is reasonably usable as well, because you're dealing with ABS plastic rather than some of the others that are maybe a little bit more wangy. I know that we had 2 SLS machines running 24/7 at Dyson, pumping out vacuum cleaners and hand dryers at the time, and we used to just have fudge factors so that we knew the nylon was performing a certain way, and what would that be in polypropylene, or what would that be in polyethylene, or some other maybe hybrid alloy polymer. So you can actually come up with these sort of, I suppose, proxy or pseudo models that you can apply, even if it's not, it's an exact science, I suppose.
yeah, and that inherent flexibility is again part of the appeal, isn't it?
Cool. Maybe that was probably a good place to finish. Thank you all, 3 of you. Save, thank you so much for being up over there in Jordan as well, and
Thank you.
Thank you, and we'll give everyone, all 3 speakers.